Okay, good afternoon. My name is Simon Poulding. I'm from the Blekinge Institute of Technology in Sweden. As you can probably tell from my accent, I'm actually British. I haven't got a Swedish accent yet. My background is I'm an academic. I research software testing. So the work I'm going to present in this lightning talk is sort of derived from that interest. And what the testing that I normally do is based around random testing. So rather than looking for deterministic values, it's about finding random values, but sensible and diverse random values to find bugs in code. And when you do that normally for typical a lot of languages, really your requirement is to find diverse random inputs, which are diverse values. But in a multiple dispatch language, really what you want is diverse values and types, because if you're going to test all the methods which implement a particular function, you actually want a variety of different types to ensure that all the different code and all the different methods is actually tested. So how do we go about that? Well, first of all, we start off with the part of the type tree that we're interested in. And here I'm just showing a very simplified version, missing out some stuff just so it fits on the screen. Part of the type tree coming below the root of the number type. And here we've got a mixture of abstract types like number and real. And we've also got some concrete types like big float and rational and so on. And also rational and complex, for example, are parameterizable types. So they have a parameter which is itself a type. So what we do, first of all, we turn that type tree into a probabilistic tree where we assign probabilities to each of the outgoing edges. And then if we want to sample a random type, we start off from number, and we just follow the edges randomly according to the weights at each of the outgoing edges. So it may be that we take this path down the tree, and we end up saying we want to generate a float 64 as one of our random values. And we do that each time we want to pick a value, so we get a different type each time. But one of the complications is the parameterizable type. So if you have complex or rational, you also need to generate a type, which is the parameter of that parameterizable type. So what we do, we extend that tree slightly by having outgoing edges from the abstract types. So now it's possible that when we want to type, start off at number, but maybe it comes out at real, and real is then the type we use as a parameter to a concrete parameterizable type. Okay, well that's half the process, but really what we want is values with those types. So it's not just sufficient to choose random types. So how do we go about the second part? And it turns out the second part is more complex. So what we want to do, we want to actually call constructor methods for those types so that you actually return random values. Now the issue is, especially within Julia, is that built-in types aren't guaranteed a constructor in the way that user-defined types are. So we still use a call. If you're familiar with the methods function, it will tell you the methods which implement a function with the name you give it. So what we do, we try and look for what look like constructor methods by doing that. So for example, if we want to construct a complex type, we will call the methods function with complex, and we might find that there's two methods which we could possibly call which look like they are constructors. But we have another problem here, which is if we're going to call those methods, we now have to construct random values to pass into them. So we need to, first of all, add those methods for the tree, but then realize that it's going to be a very recursive process, that we're going to go through this again. So we're going to have to find values for the first constructor for x, which is a real valued parameter, and we have to have random values for real and imaginary for the second constructor method. And we keep on doing that until we end up with one of the green, the types highlighted in green here, where it's obvious that you can just generate a random value using very standard methods or the distributions package within Julia. So we extend our probabilistic tree with these constructor methods as well. So this sounds like it's plausible, it might work, so let's actually give it a demo and see what happens. So, excuse me, let me show you the code first. So, the code I'm going to run is this snippet of code. So it uses the two packages which I'm talking about today, which are called data generator translators, and the data generator translator package takes a type and translates it into what we call a generator, which then the data generators package runs. I talked about the data generators package at JuliaCon last year, and the easiest way to think about it, it's a way of, it's like you can express quite complex grammars, and then the data generators package will sample randomly from that grammar. So data generators translators takes a type, looks at the type tree and the constructor methods in the way I've just shown you, and then constructs essentially a grammar which it then uses to actually produce types. So first of all, I'm going to include the packages. Then this is the key step, which is the call to type generators as a call into the data generators translators package, and it says, starting from the type subtree from number, give me a generator called numberGen. And then what I'm going to do is in the loop, I'm going to call it 20 times. I'm going to choose from numberGen, which just chooses a random number from that. So this is what I want to demo. So okay, so what I'm hoping for is 20 random numbers, which are different types on the number subtree with different values. And in fact, I haven't got that. About half the time, out of the 20 times I've tried to do this, I've had an exception raised in one of the constructor methods. And this is because the constructor methods often have a fallback to a very generic constructor which takes any as a parameter, which means that often you don't know what to pass in to actually get it to work, and it will raise an exception. So how can we handle that? This is not very efficient if a lot of our random generation process is going to fail. So what we do, we use a feature of data generators such that we can learn from its behavior. So in this case, we keep traces of the successful generation, so the times when the constructor method did not fail, and use that trace information to update the probabilities on the outgoing edges in our probabilistic tree. So in this case, we can see that it's successful going from real to rational quite a lot. So when we do essentially reinforcement learning from the traces, it updates the weights such that it tries to avoid those constructor methods which give the errors that we're seeing. So in terms of the code to implement that, it's using another feature of the data generators package where we can return the traces, we store the best traces, and then we re-estimate the probability distributions from that. So how does that help us? So in this case, what it's doing about 100 values at a time through 5 iterations. As you can see, as it gets towards the end, it learns which paths to avoid taking so it doesn't have those exceptions. So we have a much more efficient generation process where it's not raising errors within the constructor method. So we get a lot of different values here. I was dumping them out, so it's things like we have complex formed from rationals, we have int 16s, float 32s, and so on. But that's great. So we've got random values with random types coming out. But our purpose was to actually test some code. So what I'm going to do is actually going to test the plus function in Julia base. And given the mechanism we have, that's now quite straightforward because the parameters into a function are themselves a data type. So in this case, we're going to do the same process that we did before, but the plus function, we're going to test all the methods which take 2 numbers of any type. And then what I'm going to do, I'm using base test here, so I'm just going to test that they either return a number or return one of the expected exceptions, things like an overflow error, or an inexact error, and so on. So final demo is to see what that gives us. And here again, the same process is happening such that it learns from where the constructor methods are failing and avoids passing certain values into those constructor methods. And we can see the red warnings when that happens start to disappear. And in the end, in just a few seconds, we can test the add function with about 400 different random tuples of numbers. Okay, so that was just a very brief overview, but if you'd like more information, here's the details of the two packages. Unfortunately, the data generated translators package works with 0.5, but as Jeff talked about this morning, there's been some big changes in 0.6 to the type system, so I've got to find time to recode some of that. We also had a paper recently accepted or recently published at a conference using this and talking about testing Julia. And finally, if you want to contact me, there's some of my contact details on the bottom of the screen. Thank you very much.